So on page 9 of the review paper, this is the first set of problems that you haven't really been tested on yet. Up till this point, you've at least had a quiz or a test on everything so far. So this one is the absolute value section. The absolute values really they're just to show you that you occasionally run into problems where you have multiple solutions. So in this case, what we're looking for in an absolute value problem is always going to be two different answers. So in this case, when a problem has an absolute value in it, what you're looking to do is solve it in two different fashions. The first thing to do, though, however, is if you follow step 1 off of your notes, would be to make sure that the absolute value is the only thing on one side of the equation. So that's the case here. So we can go ahead and actually do a split of this problem. The equal sign is always going to be an or. And then the rest of this is to rewrite this without the absolute value symbol. And on the other side, do the same thing, except remember that it could also be equal to the negative number. So we do that as well. And now I solve this as two separate problems. I'm going to subtract 1 and divide by 2. This part gives me x equals 2. I'm actually going to do the exact same steps over here. Subtract 1. We're going to get different values because that was a negative. And divide by 2. So I end up with x equals negative 4. So you have two answers to this problem. X is 3 and x is negative 4, which means if you put either one of these numbers into this original problem, solve it, and then take the absolute value, you will get 7 as an answer. So number 63 is the same principle, but it's a little harder because the problem is not set up quite as simply and easily as this one is. We need the absolute value part to be by itself, which means that this negative 7 and this 3 out here have to go away. So before I get to splitting it up like I did up here, I'm going to take this and add 7 to both sides. Now I've got 3 times absolute value of 3x equals 9. And then I want to get rid of this 3, so I'm going to divide the whole thing by 3, which will cancel that and leave me with absolute value of 3x equals 3. Now I can actually split the problem into 2, so now I have 3x equals 3, or 3x equals negative 3. And in both cases, I divide by 3, and I'd end up with x equals 1, or x equals negative 1. So again, I noticed that a lot of people were having trouble with this problem in class. It turns out it's actually one of the easiest absolute value problems to do once you really get it down to the absolute value part of it. It's getting rid of the other stuff that people tend to either forget or make mistakes with. So you want to make sure, again, that you never split the problem until the absolute value is the only thing on one side of the equation. So we're going to keep that rule in mind about having the absolute value by itself and the splitting and all that, except that with an inequality, it's a little bit more complicated, only because the inequality symbol makes it just a little bit more tricky. One extra thing you have to remember. So again, this absolute value is all by itself, so it's ready to be split. This greater than symbol tells me that it's going to be an OR type problem. So just like before, I'm going to recopy this exactly as it was, except on the other side, when I go to rewrite it, instead of just making that number negative, I actually have to flip the inequality symbol around and then also make it negative. So that's the other little trick to inequality. But now I'm going to solve these as if they were equations, more or less. So I'll add 7. And divide by 3. I end up with x is greater than 5. Or, on the other side, I'm going to also add 7, but I'll end up with a different answer because the number started as negative. Divide by 3, I get x is less than negative 1/2. It's okay to have a fraction as an answer. When these problems are more complicated, it occasionally happens. So if you notice on your review paper, there's a little note over here that said all your inequality answers need to go on number lines also. So you need to draw a number line, make it very simple, put the 0 in the center. Now I need positive 5 on there, and I need a negative 1/3. So somewhere over here, I put a negative 1/3. So I want to shade for greater than 5. That means an open circle on the 5 and shading like that. And this one, I want to shade for less than negative 1/3, which means an open circle on that and less than shade to the left. Like that. And that problem is done. Okay, so let's look at 65 under the same context then, except knowing that it has to have the absolute value by itself. This divided by 4 part has to go away, so we cancel dividing by multiplying. And we'll be left with 9x plus 1 less than 8. So because the absolute value is by itself, I can split this into 2. So I have 9x plus 1 less than 8. A less than symbol tells me it's going to be an and. And so then the other side is 9x plus 1. Now I'm going to flip the symbol around and make the number negative. So I'm going to subtract 1 from both sides. I got 9x is less than 7. Divide by 9 and I get x is less than 7 over 9. Again, fractions sometimes happen. Over here, I'm going to subtract 1, which gives me 9x is greater than negative 9. Divide by 9, and I get x is greater than negative 1. So again, I'm looking for a number line type solution. Put a 0 here, I got a negative 1 on there. I need a 7 over 9 on there, which would be on this side. So, shading. We shade the first one, which is less than 7 over 9. It'll be an open circle here, and shading this way. If I shade the other one, which is greater than negative 1, it would be an open circle here, and shading this way. Now what I actually want, because of the and being a conjunction, I'm looking for overlapping shading. So what I really want is where it's both orange and green in this case, which is in between the two numbers. So I would highlight it like this, and these are open circles because they're not colored in by both numbers. So the actual area that I want is just between negative 1 and 7 over 9, not including either of those numbers. And this problem is done. Okay, this time, what we're going to do is take a system of equations. This is section 3.1. And all we're doing is going to see if this number, this coordinate point, is the solution to the system. That means, is it the one coordinate point where the system has a common solution? That means that it's a good answer for both. So, I'm going to take this equation, and I'm going to put a 4 in for x and a 5 in for y. So the 4 for x and the 5 for y. And I just want to see if it works out. So, I'm saying 4 minus 6 times 5 equals negative 26. Well, 4 minus 30 is negative 26, so it works. That's a good one. So if the other one works, then we can say yes, it's a good solution. If it doesn't work, then we still have to say no. So again, I'm putting the 4 in for x and the 5 in for y. If we don't do that last one. This is 8 plus 5 is 13. Equals 13. So again, we have a good one. This is what it takes to prove that something is a solution. You need to show the substitution step, and then finally show that it works out in both cases to say yes. So again, in this problem, same idea. I'm checking the solution. I'm going to put 0 in for x and 3 in for y. So I have 0 plus 15 equals 15. This side is 15, and so is this one. That's a good one. And again, 0 for x, 3 for y. So I end up with 0 minus 3 equals negative 3, and that is also true. So it turns out that both of these are yes type solutions. Now, the thing you want to watch is when you go to do these, if you get one that doesn't work, it's automatically false. So to prove something true or to say yes, then you need both of these things to work out, and you have to show both. If you get one that doesn't work, you can automatically say no, it's not a solution, and you don't have to continue proving the other one. It only takes one false answer to make this a no solution. That's the end of page 9.